All right, let's welcome to 13.2, which is a section on line integrals. You may also consider it like a path integral because we don't necessarily have to be on a straight line. In fact, our first example is not going to be a straight line. So let's just start by taking an example. Let's take the integral over c of 2 plus x squared y ds. Okay, now first let's talk about what is going on here. So we're going to actually say what is c. Of course, I guess we're always talking about what's going on here. Sorry about that. I don't like being on video. C here we're going to take to be the upper half of the circle, x squared plus y squared equals 1, starting at 1 comma 0. Okay, so I could actually understand that to be given by x of t equals cosine t, y of t equals sine of t, where t goes from 0 to pi. Okay, let's just draw that in. Okay, we start here, we go around, and we end here. Okay, so next thing we should ask is, what about this ds? Well, ds is the arc length. Well, actually, it's the differential arc length, but we know that from before to be the square root of, let me write it this way, dx over dt squared plus dy over dt squared with a dt out there. Okay, so now when we do this for this path, this is going to be the integral from 0 to pi 2 plus, now instead of x, we're going to write cosine of t, because that's what x is along this path. Times sine of t, because that's what y is along this path. Okay, let me move this a little bit to give me more space. Now, we're going to have the square root. Now, in this case, x prime is going to be negative sine of t squared. Let me write that a little better. Plus derivative of sine of t is cosine of t squared dt. Now, this, of course, collapses to be 1. Okay. All right, so we end up having, guess I should have put this in parentheses here, the integral from 0 to pi of 2 plus cosine squared of t sine of t dt. And I'm going to let you guys figure out that integral. That's a pretty standard one. 2, you should be able to integrate without any problem whatsoever. And cosine squared of t sine of t, you should be able to integrate with very minimal work, letting u be cosine of t. Okay? So, for you to finish. Okay? All right, let's talk about line integrals for vector fields. Okay? just a slight difference. There, what we're going to do is we're going to actually we're going to be having the integral over a curve, f, and then we're going to dot it with dr. Okay, so now, if the curve is given by r of t, so that's some, x of t, y of t, there might be a z of t in there as well if we're in 3 dimensions. Okay, then this is going to come out to be the integral from some beginning time to some ending time. Ti is initial time, tf is final time, of f. The input is the curve dotted with the derivative of the curve with a dt there. I don't need a dot there, so let's... Okay, so let's do an example. Let's take, for example, f of xy equals x squared y squared. Okay, along the curve, x squared plus y squared equals 4, starting from the point 2, 0 to the point 0, 2, and then followed, oh no, we're really going crazy, by the straight line zero, 2, 2, 4, 3. Okay, so let me draw that out. Okay, so we start out at 2, 0, and we go to 0, 2 as a circular motion. Okay, then we go to 4, 3 in a straight line motion. So we go like that. Okay, I'm going to call this C1. I'm going to call that C2. All right, for curve 1 and curve 2. Okay. So let's first write out the parameterization. Okay, so C1, hold on just a second here, sorry. Give me just a second. Sorry for the dead time. I'm trying to make my notes that I'm going off of a little bigger. All right, so now we're here. C1 is, well, x is going to be 2 cosine t. Y is going to be 2 sine of t. And here t goes from 0 to pi over 4. Okay? Now we're going to have a C2. C2, well, if I think about this line, it's got a y-intercept of 2, right? Y-intercept here of 2. And as it goes over 4, it goes up 1. So that's a 1/4 slope. Okay? So I'm going to write this as x equals, now I could name it something else. Let's call it tau. All right? And y is going to be 1/4 tau plus 2. And tau is going to go from 0 to 4. Okay, so what I'm going to do is I'm really just taking each piece separately. I'm going to take this piece, and then I'm going to add this piece to it. Okay, so our integral ends up being, or when I got a space? I got enough space. Okay, our integral is going to be, let me bring that down. Our integral is going to be the integral from 0 to pi over 4. That's the first part. Okay. Remember our curve was x squared, y squared. I'm going to write it as a vector. Dotted with, now, r prime. Let me just write it. Let me write it this way first. Sorry. Really going crazy today. F of r of t dotted with r prime of t dt plus the integral from 0 to 4 f, let me write this as r of tau, put like r1, r2 actually, let's make that r1, dotted with r2 prime of tau. Now, you don't really need to change the variable because it's inside of the integral, so it doesn't really matter. But I just wanted to do it just so that we have different integrals here. So our f, remember, is x squared, y squared. Okay, so we're going to take each piece. A little hard, I can't see everything I'm doing. Remember that 2 cosine, 2 sine. So here it's going to be, let me write it down. Okay, R1 is 2 cosine t, 2 sine t. R2 is tau, 1/4 tau plus 2. Okay, so now we're going to have from 0 to pi over 4. Instead of x squared, y squared, we're going to substitute these expressions for x and y. Okay, so we're going to have 4 cosine squared of t times, okay, now r prime is going to be, let's write it this way. Let's write it in dot product form first. So 4 sine squared of t, that's f, dotted with r prime, it's going to be negative 2 sine of t, 2 cosine t, okay, dt, that's the first integral, plus the integral from 0 to 4, x squared is going to be tau squared, y squared is going to be 1/4 tau plus 2 squared, and r prime here is 1/4, and then we'll have d tau. Okay, just set up what the integral is, and then I'll let you guys handle the rest. So from 0 to pi over 4, that's going to be negative 8 cosine squared of t sine of t plus 8 sine squared of t cosine t. All right, dt plus from 0 to 4 tau squared plus 1/4, And then you just take 1/4 tau plus 2 and square it, whatever that is. Okay. I think we can all agree that this integral is completely trivial. You just have to do this expansion. This integral is pretty much trivial. You just let u here be equal cosine t, u here be sine t, so you just split them up. Okay. And you can finish the rest. All right. With that, we'll see you in the next video.